Hello, my name is Benjamin Lin, and today we will be going over the Lindemann mechanism. Now, this problem hasn't shown up on past US NCO exams before, but very similar concepts have, and I can almost guarantee that it will show up sometime in the coming years. Now, because no past problems do exist, I had to come up with my own that I've posted on my YouTube community tab. Be sure to check that out. But I've also copied it over to right here. So let's get started. Eric runs a kinetics experiment where some gas, A, converts into the product P. He runs the experiment through multiple trials with low partial pressures of A. Eric determines that the rate is second order with respect to the concentration of A. Aldrich does the same experiment except at high partial pressures of A. He finds that the rate is first order with respect to the concentration of A. Then, Ben comes along, and he has faith in his fellow chemists and believes that they are both correct. He proposes a mysterious explanation. And then, to confirm his hypothesis, he runs the experiment at low partial pressures of A, and then he adds an inert gas, so one that does not participate in the reaction, to the reaction vessel, and finds that doing so accelerates the rate of reaction. This finding confirms Ben's idea and supports the fact that both of his friends are correct. What is his explanation? So, if you haven't gotten a chance to think about this on your own, I encourage you to pause the video and think about it. But I'm going to be moving on right now. Now, this question is really asking us about the Lindemann mechanism. So, the Lindemann mechanism is as follows. Some molecule, A, is going to turn into the product P. However, in order to do that, it needs to reach a higher energy state, and some activated form of A. And that's what we're going to call A star. And in order for the molecule of A to reach the A star point, it needs to collide with another molecule that's able to provide A with that energy. So that other molecule is going to be denoted by M, and this can be either A or another molecule. So first, let's just derive the rate law for this equation, and we'll see how this applies to the problem given. So this is how it goes. First, we know the rate of reaction is the rate of formation of the product. And we know, let's call this K2. We know that this is going to be equal to K2 times the concentration of A star. However, we know that we can't have intermediates in our final rate law, so we're going to need to find an expression for this intermediate. So what's going to help us out is the steady state approximation. And what the steady state approximation does, it assumes that the intermediate maintains a constant concentration throughout the reaction. So that means the concentration of A star does not change. And in order for that to be true, the rate of production of A star needs to be equal to the rate of consumption of A star. So the rate of production of A star, let's call the forward reaction K1, the reverse reaction K minus 1. The rate of production of A star is going to be equal to K1 times the concentration of A times the concentration of M, right? That's just the forward reaction here. And then the rate of consumption of A star is going to be the combination of the reverse of the first reaction, where A star goes back to A, and the second step of the reaction, where A star goes to P. So that's going to equal K minus 1 times the concentration of A star times M plus K2, that is the concentration of A star. Then, using the steady state approximation, we know these two rates are going to be equal to each other. So we can say K1 times the concentration of A times the concentration of M is equal to K minus 1 times the concentration of A star times the concentration of M plus K2 times the concentration of A star. Oop. Then what we can do is isolate this concentration of A star term, so we can plug it back in to our equation up here. So if we do that, we get A star is equal to K1 times the concentration of A times the concentration of M, and this all divided by K minus 1 times the concentration of M plus K2 times the concentration, nope, just plus K2. Then if we plug this form of A star into the equation up here, we're going to get dP dt equals K2 times K1 times A times M divided by K minus 1 times M plus K2. So this is our final rate law. And let's see how it applies to the problem we have above. Now, in these two experiments run by Eric and Aldrich, there are no other molecules other than the gas A inside the reaction vessel. Therefore, we can say that the identity of this other molecule M is actually going to also be another A molecule. It's just another A molecule colliding with the first A molecule to turn the first A molecule into the A star excited state. Just so this will also be A as well. And if that's the case, right, we can replace M in our rate law here, and it will look like just K2, K1 times A squared divided by K minus 1 A plus K2. All right, and then we can evaluate if it makes sense, the data that they got. So what I mean is, we saw that there's low partial pressures of A. The rate is going to be second order. Well, if the partial pressure of A is very low, that means the concentration of A is also probably very low. That means in the denominator here, K minus 1 and A plus K2, the K2 is going to be significantly greater than K minus 1 times the concentration of A. Therefore, the denominator is effectively just K2. And if the denominator is just K2, that means the rate would just equal to K2, K1, A squared over K2. These two cancel out. And we just have K1 times A squared. And we would observe our second order kinetics. Now, on the other hand, Aldrich does this experiment at high partial pressures of A, and he finds first order. Let's see if that matches our rate law that we derived. At high partial pressures of A, the concentration of A is also going to be high. And we can assume that in the denominator right here, the K minus 1 times the concentration of A is going to be much greater than K2. Therefore, the denominator is effectively just K minus 1 times A. In that case, we can rewrite the rate law as K2 times K1 A squared over K minus 1 times concentration of A. And then this is all just one constant, and this A will cancel out with this exponent up here, and we just have some constant times the concentration of A, and we will get first order kinetics, and this makes sense. Now, many of you have probably seen this motif a lot before, but the kicker is that there can be some different molecule M. It does not matter what the identity of this molecule M is. And that's why when we added some inert gas to the reaction, we will accelerate the rate of reaction as we are providing more chances for collisions to occur, and that will create more molecules in the A star state, increasing the rate of reaction. So the correct answer to this is the Lindemann mechanism. That concludes our video on the Lindemann mechanism. Please be sure to check out my YouTube community page, where I will be posting problems like this, If you enjoyed this video, please be sure to like and subscribe. And thank you for watching today.